let's give it under 1 minute. Okay, cool. Let's get started. So this lecture will be a continuation of the last lectures, where we discuss some initial motivations for diffusion models. So just a recap: last time we introduced variational autoencoders and variational inference, where we have some way of modeling the joint distribution of observed data and observed latent with like an effective way of training and doing inference with variational inference approach, by basically trying to approximate the posterior of Px given Z with the neural networks. And we also introduce energy-based models, which are essentially very intractable if we care about the precise energy, and but we can get around with that by doing smarter sampling. And so the score-based model, as we motivated from Langevin dynamic sampling from a given energy-based model, which essentially instead of learning the precise likelihood defined by the energy, we follow kind of the gradient of the density function, so as we can still do like exact sampling from the distribution. So we're kind of matching the score or a vector field defined by the gradient of the probability density functions. And effectively, training that does not require access to that function at all, and it only requires adding noise to data and predicting the noise back from the data points, which is kind of like a magic for the score matching. So the follow-up of that is this DDPM framework, where essentially we just forget about all of these score matching theoretical groundings and just try to define a progressive a Markov process, a discrete MDP, where each step we try to add some noise, and we have precise way of controlling this noise. So we basically have a fixed or already known encoder that corrupts the data from clean to noise, and we try to learn the inversion, basically a hierarchical decoder that try to invert that process, and at the end we'll be able to generate data that match the data distribution if several assumptions hold. And for diffusion, there are actually very particular way of designing the progressive noise adding process, which is the forward process, essentially controlled by these scheduling of noise. And this is kind of particularly form of the forward process. And we try to invert this process by training, again, like a hierarchical conditional probability models, which is again another Markov process. So the key idea is to use the model to learn these transition matrix, and in a high level that approximates the score of the underlying function. And again, like even though we're using probability here, but at the end when we actually plug in this Gaussian assumption of the process, we ended up knowing the exact form that we can parameterize our network. So we ended up using this loss function here, where each time of training we sample a noise and we sample a time t. We sample clean data, we sample a time t, and we kind of crop the data by using the known schedule. and we just directly predict the training a denoiser that try to predict back to try to invert that correction process by doing these score matching loss. So if we look at the training procedure, essentially we're sampling data, sampling a timestamp, sampling a noise, and we have this precise form where we basically try to compute where we are at timestamp t using this conversion here. And you can consider that as like at the corrupted data points, we try to predict what the noise is at that particular data point and the given time t. So in the sampling, during sampling, we're kind of doing the inverse of that, where we start from the completely noise, and we either follow these kind of discrete Markov sampling process, but in practice, you can consider that as a discretization of a continuous stochastic differential equation. But by each time we are making, we're going one step towards where we predict the denoised direction should be. And then after taking that step, we also add slightly small perturbation to my current positions by adding this additional noise function, which is what kind of Langevin dynamics used. And by doing this for multiple steps, I kind of ended up getting very close to the true data distribution at the end. But I think that the important idea here is we have to remember that all of these conclusions that we arrive here depends on a very particular definition of noise adding and denoising process, which is the Gaussian family. And it has underlined this process, there's specific definition of what the noise is and what the model is used for that, which enables us to arrive in the score match, this score function and score matching loss. An architecture, actually this is a little bit outdated already, that in the computer vision domain, people use to train the diffusion model is called UNet, which essentially in the diffusion, we're considering this hierarchical variational inference where each time step, the latent variable xt has the same size and shape as the previous time step. And therefore, we want a network to be able to input and output the same data with exact same shapes, such that they can be added, and we'll kind of consider that as like predicting where your next steps are in the same input space. So the UNet architecture basically try to mimic that behavior where we can consider in computer vision we use these convolutional neural networks to downsample and extract key features from the current time step, and we do up convolution at the later half, such that we can revert it back to to have the same dimensionality that match the input shape. And more importantly, because our score function here depends on the time. Basically, we're reusing the same neural networks to learn the score function at different time steps. So essentially, the score function needs to be conditioned on time. And in this initial UNet architecture, the time is passed into each layers of the UNet by kind of doing kind of like you have this additional embeddings from the time. We call it time embeddings. That is added to the features, and we can consider like a more complex way of aggregating the time informations, for example, with attentions. And this is proved to be quite effective in earlier days of diffusion for computer vision. But I think right now the more advanced architecture is called diffusion transformer. So I apologize that I have not included the slides on that. I'll make sure including that next time. But instead of using these kind of convolution and up-convolutional filters, we just directly use the transformer model over the entire input. And the way it factors in the time information is by introducing the special type of layer norm, called adaptive layer norm, where you embed the time steps with time embeddings, and you use that to adjust the scale and the bias. Basically, you're kind of adding some shift and different scaling to each layer of the activations, and that the scale and the shift is determined by the time. So that kind of special mechanism of adjusting the activation makes it effective architectures, makes this kind of an effective inductive bias for learning the score functions, which usually kind of adjust what it focuses on at different times. And you can consider that scaling is helping us to kind of tell you at each time step where you should be focusing on, what kind of information you want networks to focus on. Yeah, I think it's just called diffusion transformer. It's kind of an extension of vision transformer. Yeah. And I will include a slide on that next time. I apologize for not doing that. So if we take a deeper look of this kind of sampling process, right? Right now we're intentionally setting up this discrete schedule of this discrete Markov process, right? At each times we use this discrete time step from 1 to t, and we learn like a set of transitional matrix. But in effect, the time does not need to be discrete at all. And if we consider like having unlimited number of time step from the noise to the clean data, right? You're basically doing kind of a very continuous transformation of the distributions. You're basically making these continuous movement or jumps in this vector field defined by the underlying energy, such that at the end of your movement, the trajectory you landed, you ended up landing in a sample from the target distribution. So from this kind of this discrete view to just basically try to shortening the delta t, and at the end we can ended up having this very smooth and fully continuous transition trajectories, where instead of sampling a t from a set of t's, we can do kind of a uniform sample from 0 to 1, or like 1 can be basically at the ending time point. And we're still learning these forward and backward diffusion process, but instead of like having these discrete Markov process, we try to just treat that as a continuous time transformation. So this will give us kind of a novel interpretation from the point of stochastic differential equation, where you can basically, if you look at what we're doing here, right, each time you have an xt and you predict where you are in the future, where you landed up as the next xt. So essentially you're kind of moving your data in the input space by pushing it forward with some kind of forces or like drift. So that process can be defined by a stochastic differential equation, or SDE, where the first term is kind of the deterministic drift defined by the underlying force or energy landscape, and we also have this kind of additional noise added to the movement. This is simulating in physics, where like, you have this Brownian emotion that's purely random noise caused by like the random movement of particles decided by thermodynamics. And we're also like making sure that if we're moving with the rules here, we ended up landing in the sample space, where if we look at the samples we get out of these trajectories, we ended up having a sets of points that represent the probability density function. And if we train it well, this probability density function should kind of match the true data distribution as much as possible. If we look at if we take this SDE view in the diffusion, right, we can basically consider the forward process, the forward noising process, as a forward SDE, where you can just blindly adding noise to the data, and the reverse sampling process. The sampling process can be defined by this reverse stochastic differential equation, where the kind of the velocity that's driving the fixed drift term can be defined by this score function of the underlying distribution, and we're adding this noise to kind of mimic this again like Langevin dynamics kind of behavior. Although like in real world, we won't be able to do fully continuous computation due to numerical issues. So at the end, we'll be solving this process with some level of discretization. For example, with certain SDE or ODE solvers, where we still need to like pick a very small time step and go like kind of a straight line within that small time step to mimic this continuous trajectory. But taking this continuous view gives us a more flexibility into the like training of the diffusion model, where essentially instead of doing this discrete time step sampling, we're doing this uniform sampling from a continuous time region. And also like we can understand the noise at different time step being a continuous process defined by the underlying diffusion process. Basically, we can now rewrite our score-based function into this kind of function of x given t, where t is a continuous value right now, and if trained while, it should approximate the score of the underlying distribution at time t. So the t here basically tells us the noise level you're at in the like the score space. And the training is essentially the same as previous version, but instead of having a discrete t, you kind of have like a continuous t. And the sampling now, like we're now sampling, instead of doing a fixed number of steps, we have kind of this continuous view of solving an SDE, where if we use an adaptive step size solver, you could end up using different number of steps when rolling out these samples, and the solver can automatically decide the step size and like how much movement I want to make at each time point. So one such solver is called Euler-Maruyama solvers. It's kind of like the Euler solver, but with also taking into consideration this like additional like diffusion noise terms. And how it realizes, again, like doing some level of discretization of the time steps. Cool. So is everyone good on the diffusion? All right. That's great. So so today we're going to talk about a different family of models, which we start from a completely different motivation in the history, but it ended up being a very interesting method that shares a lot of analogy with the diffusion process, and we believe that this line of family is kind of more is a more generalized family, and it shares some benefits compared to a diffusion model in terms of the generalizability of the model and flexibility, and it also enjoys benefits like ease of training in certain cases, not always. So if we take a back look at the families of generative models we care about, right? So essentially, we talk about generative model being tried to mimic the data distribution with neural networks, and we also gradually move into the direction where we just don't care about the distribution, but we want a model that is able to give us samples that mimics the distribution. So this kind of starts the line of mindset where if we can sample from something we know, like noise, Gaussian noise, and we try to transform or map our samples to another space where by doing particularly mapping with the neural network, we're ended up sampling from the true data distribution. And this transformation or the mapping function is what is important in defining all of these generative models or generators. And how we set up our generators and our loss functions basically kind of define the different families of generative models. For example, in variational encoders, we have particularly defined these variational structures and using ALBO to still approximate the likelihood in some degree and try to do the maximum likelihood estimation or using the ALBO. So like different types of models enjoys different types of properties. For example, the autoregressive model, you can basically solve the exact likelihood if you can, if the underlying data is indeed factorizable. Variational autoencoder is kind of a little bit more general, and it has the benefit of learning explicitly this latent structure, which gives us some information about representational learning. However, the marginal likelihood on P of X, which is what we want to model, which is the data distribution, is not exactly tractable. So we can always estimate that, approximate that by doing some kind of marginalization or amortized marginalization, but it's not always exactly tractable, unlike the autoregressive models. So this motivated the line of method that we're going to talk about today, with the mindset that we want kind of a model that is able to do this transformation between the latent variables that we can control to the actual sampling space, but at the same time we want to exactly track the likelihood of this transformation. And the question is like, how is it possible to do that? And the answer is yes, for actually a very interesting family of models that we'll talk about today. The goal here is to kind of train a generator that is both easy to sample, where we know exactly, like with the forward pass, we sample from Z and we get a sample from our distribution. At the same time, we have some closed form solution of what the likelihood of my points are. And the key idea is to make this mapping from noise to the data invertible. And by invertible, so basically the invertible function means if we have a function f defined between f, z, and x, that function needs to, the inverse of that function needs to exist, such that basically when we apply f to z, we get x, and we apply the inverse of f to x, we get z. A lot of the functions are kind of the simple functions, like for example, linear functions, exponential families they're invertible, but not all neural networks are invertible. So this line of method called normalizing flow or flow model basically try to come up with first of all a model family architecture that is defined to be invertible, but at the same time we also want to know how to compute the likelihood of the data points when we make this conversion from z to x. So this is not a simple task as we thought. So and why is that? Because so first of all, here x and z are both lying on the high dimensional continuous space. They can be discrete, but we consider a general case of x and z being continuous, and they have to have the same dimension, which is usually all the invertible function needs to fulfill. And essentially, what's the key the key part of this model is the rules that we can use to compute the likelihood of after the transformation, if we know the likelihood of where we start. So why is that? Because if we're sampling from the P of Z, where Z is the Gaussian noise, right? We will immediately know the likelihood of the point that I sample because I know exactly what the distribution of Z is. However, once we apply this transformation to X, we can consider that the points get scattered into a different data manifold or data space, and the place where you ended in does not have the same distribution or density as what the density is in the distribution of Z. So by applying this rule, which we call change of variables, we essentially tells you basically for every point x that I get, which I get that by transforming from a z, I can use the likelihood of z to compute exactly the likelihood of x. And this change of variables defines the rules of how that is computed, essentially depending on the probability of the noise sample times this by the determinant of the Jacobian of this transformation function. So I will get into detail of that in a bit. But yeah, basically the sampling procedure is very straightforward. We sample a noise, we apply this transformation, which is defined by this f inverse of z, and we try to train this network such that we kind of match the distribution of the data distribution. And in the inference time, we can also apply this change of variables such that for every point we sample, we know exactly what the likelihood of that point is. So there are a couple of mathematical concepts that we need to talk about before getting into changes of variables. But so the first is to give us a kind of an intuitive, like to give us some intuition like why that change of variable is needed, right? Think about two tweak cases here. Like the first tweak is, like let Z be, let's consider some like a uniform random variable. Let's consider like kind of a discrete space. So if we define the uniform distribution from 0 to 2, and we ask like what is the probability of Z being 1, this is a continuous density function. Let's say like if you define a uniform distribution in the region of 0 to 2, right? So the example here has a function of 0 to 1, but you can consider extending that from 0 to 2. And if you ask what is the probability density of Z at a point 1, or actually any point from 0 to 2, that should be 1 over 2, considering the total like volume of the integral of the probability density from the region, the domain 0 to 2 is normalized, so it's always 1. We can solve these. We can do a quick check that the density is 1 over 2, such that we can, at every point, if you have the density of 1 over 2, after doing this integral, you get 1, which is kind of the marginalizing all possible values of that distribution. So now, if we transform this distribution by a simple function, like basically multiplying Z by 4, right? Now, like if we ask the question, what's the probability of X if X equals to 4 times Z? Then, like, a very naive way of solving this is like I just plug in. I just solve for Z. So if X equals 4, Z equal to 1, and I just use the probability of Z equal to 1, the density of Z equal to 1 for my P of X. But this is actually wrong, because if we look at this uniform distribution defined over 0 to 8, in order to have the density function that is normalized to 1, if we integrate it from 0 to 8, the solution of that density function should be 1 over 8 and not 1 over 2. So this is another example here where you can consider you're transforming something within the uniform distribution between 0 to 1 to something between 1 to 3. So even though we kind of, so the intuition here is because we extend the, by doing this transformation, your points are now scattered to be like distributed into a wider range of value regions. So enable to keep the integral to be the same, which equals to 1, we have to reduce the density of all the places by a factor of 2, such that the densities after this transformation is still a valid probability density function. So here you can see that we cannot just simply plug in the solution of the inversion of the function and use the probability density from the source. Instead, we also need to consider the volume change, basically because you're spreading out your distribution into a larger region, so you probably now becomes a thinner probability. Your density function becomes thinner, and we call this kind of the preservation of mass, which is the key idea behind this change of variable formula. Is this clear to everyone? Yeah, don't be shy. Like if you have questions, raise your hand anytime. Okay, so this is kind of the uniform. When we talk about the special case of a uniform variable distribution. But what if we have like more general distributions, right? So, but like for any distribution, you can basically consider this small. You can slice the distribution into small pieces, and at each time you basically try to transform between these two pieces, and you want to make sure that similar mapping and the change of variable formula is fulfilled. So in this very simple 1D case, right? So suppose we're taking this very small slice of the distribution, which we can call it delta Z, and we're transforming that mass to another small delta region in the target domain. What we want to preserve is this volume of the two density functions, such that this the volume of the blue square and the green square is equal, or the area, because it's kind of 1D. So essentially, we have this equation here, which if we move things into one side, we have what's called derivative of z given x, where if z is the function of f inverse 1, we can have the derivative of x in f inverse with respect to x. And that's kind of the simple case where you can convert pi of z, which is the density of the source sample, into the density of the target sample by multiplying this kind of additional absolute value of the gradient of f inverse with respect to x. Everything okay? Okay, now so this is a 1D case, but in the actual, a lot of the actual functions are high dimension and extend beyond 1D case. So for example, if we look at the 2D case and beyond, we essentially relying on the computation of a determinant of the Jacobian matrix, where the Jacobian matrix for a high dimensional function can be defined by basically the partial derivative between the function, each dimension of the function with respect to the counterpart on the input variable. So this is kind of the Jacobian. If we have the function of x1 equals to z1 plus z2 and x2 equals to 2z1, we can write it down as a matrix, right? And we essentially have derive this Jacobian of these linear function families, and we can get the inverse Jacobian matrix as well. And then an important property is that the product of the two equals the identity matrix. And the other important mathematical concept is the determinant. I guess, yeah, if everyone's taken the kind of the linear algebra, you'll be familiar with the determinant, which is a metric defined, a value computed out of a given matrix, mostly squared matrix. And by doing this kind of the cross product, and what it gives us is effectively, you can consider this as kind of the area, the size, or the volume of the parallel that it's defined by this matrix. So essentially, we can define that over any matrix, and including the Jacobian matrix. So we're kind of getting the value, the volume of this Jacobian matrix, which kind of assembles what this part is doing in the 1D case. It's natural extension to high dimensional space. So let's say if we now have a 2D change of variable formula where we can consider extending the 1D by introducing this matrix of delta x, right? And if we look at the determinant of these, we want the volume from the left-hand side to be preserved after this transformation. So we have this equation here which tells us the preservation of mass. If we just move things around and do some transpose, we can get this. We ended up having this Jacobian matrix and the determinant of Jacobian matrix, which gives us these formula here, which is what we use to compute this transformation of density between high dimensional distributions, z and x. And the inverse of that is also defined because the determinant of the inverse is kind of the 1 over the determinant. Okay, we're good. Okay, so given this rules that we define, we'll be able to basically define a transformation at the same time also exact formula of suppose if we have a continuous transformation function x, where I think there are several limitations that first of all it has to be invertible and it has to be continuous, and we'll be able to define this general change of variables between x and z, which are linked by this invertible function, and we can see that this is kind of this is a very straightforward generalization of the 1D case, and it's different from VAE because in VAE the z is usually like Z can have like much lower dimension than X, but here we're converting between the same dimensionality of X and Z, and it has to be both continuous. And and finally you have this conversion of determinant of the inverse and the inverse of determinant, which can be used to do like conversion on both directions easily. So basically the normalizing flow model is formally defined as kind of this family of models where we try to parameterize a mapping from X to Z with a family of invertible functions. It is a deterministic mapping in that once we know Z, we know where X is exactly. And we will be able to, in the inference time, we'll be able to sample effectively by sample a Z and transform it to X, and at the same time we get the exact likelihood of P of X by applying the change of variables. So we can imagine like doing one-step transformation being tricky if the data distribution is kind of very EO-shaped. So you can also stack the flow models. It's kind of like the residual neural networks where you can stack multiple layers and do multiple transformations. You can choose to reuse the same network and doing it for multiple steps as well. You kind of unroll one layer of continuous normalizing flows to multiple layers of continuous normalizing flow that gives you this chain of transformations, which will be able to still compute the change of variables if we chain them together. And we'll be basically applying this chain of change of variables, such at the end we're still able to compute the likelihood of the final output given the initial noise in the model. So this is a very this is great that we can expand the expressiveness of our model and expand the family that a model family we can use to do these transformations, and we're still able to exactly compute this likelihood. Okay, so now that we have these formulas, right? One naive way, like one straightforward way, is to train the model is, of course, maximize likelihood, right? So for any given data, training data, like we can try to like learn this map. We basically learn this mapping from noise to the training data, and we apply this chain of change of variable functions, and we get exact likelihood. We can directly like train our model parameters to optimize to maximize the likelihood on this data. And this is better than the variational autoencoder, where we have to rely on this variational bound, which is not always guaranteed to converge. And the sampling is also very straightforward. It's just like kind of like the decoder in variational autoencoders, and you can do this stacking of multiple layers. And at the same time, at each layer, you still get this transformation of X to Z, so you still get this ideal latent representation space. But this is, everything sounds like great, right? It's like a fantastic model that gives us everything. But has anyone realized a very critical downside of this model? Anyone want to try to take a guess? Sorry, what's...
Could the Jacobian have a zero determinant of zero?
You mean the corner cases where you have numerical stability issues?
Yeah.
Yeah, I think that's one of the concerns for sure. Anyway?
It's very hard to calculate the Jacobian.
Yeah, exactly. So this Jacobian computation is, we talked about last time actually, it's actually very expensive, and in the score matching, when we talk about score computation, it also involves this Jacobian computation, which is kind of the OD computation, and we have to do it for every points between high dimensional points and multiple layers of this transformation, and this can both gives us very inefficient training efficiency, because we have to basically roll out multiple steps and do this push forward or change of variable functions, and we also have to back propagate through this determinant of Jacobian function, which makes it even more complicated. And as you mentioned, like there could be error that's accumulating in this training process when you do these multiple steps of conversion. And this is what we call simulation-based training of the normalizing flow, where you can essentially considering this this forward process of computing likelihood being kind of, you have simulated the entire process of transformation, and you have to backprop through that chain of transformation, and that means you need to backprop through these determinant of Jacobian functions. So a lot of the work on this field focuses on like how we can make the Jacobian computation more efficient and make it like more sparse by configure the function that rely on only a small part of the variables, and so you have like a sparse you have some sparse structures in the Jacobian, which make the computation easier. So yeah, and then the other thing is we need invertible functions, and this is not something that's always guaranteed, right? So and there are several lines of work on this field try to come up with known invertible functions. Like of course, always like the simplest way is always to do this linear kind of a linear function, which is of course very invertible. And we can also define exactly what the Jacobian is, which can also be like very simple to compute. We have solutions. And if we want to add some nonlinearity on top of the linear, we have to be careful here because not all like nonlinearity is invertible. So for example, only use kind of 10H function, and making sure that your things fulfill constraints such that the inversion and determinants is not EO defined. So this is kind of the example of using this, we call it planar flows, like basically a simple like MLP-like flows, and you can see that it's kind of effectively like you're splitting up the space into smaller chunks of points or clusters. So by stacking layers of planar flows, we're still able to converge to like some representative distribution of the data. And another architecture is called additive coupling layers. It's actually a very smart idea. Basically, if you have your variables, you try to dissect your variable into two disjoint sets, where for the first half, the mapping function is just exactly what it is. You pass forward what access into the next layer. And then in the next, and then later half, the function is defined as yourself plus the transformation that's applied to the first half of your model. So the reason we want to do that is if you kind of subtract to the left, it can easily get the inversion of the zd plus 1 to n to xd plus 1 to n, because if you basically you minus this transformation of z1 to d, and the z1 to d is exactly the same as x1 to d, so you kind of also have this by design invertibility of the model. And we can also define the Jacobian matrix, which is nicely a lower triangular matrix. So this is kind of like the architecture of one layer of the adaptive coupling layers, and yeah, we can see that it's very, very similar to basically a residual network. Instead of basically the first half can be considered as kind of the residual part, and because we have to split it into two, and we don't want to only like pass only the fixed half of the features. So deeper in the network, you can basically shuffle around the dimensions, such as you get like different features being bypassed each time. But but the shuffling is also an invertible operation. So like you effectively can stack this kind of resonant-like layers, and you will be able to invert through that layers to. And the nice thing about this, another nice thing is if we design it carefully, we can get a Jacobian naturally, which always equal to 1. So the inversion, like the volume preservation is like naturally held. So yeah, another line of work that I think that the intuition here is try to make autoregressive models more expressive and powerful by leveraging this kind of normalizing flow transformation at each step of the autoregressive model. It's called like autoregressive flows or masked autoregressive flows. But essentially what you try to do is like considering each step. At each step of your decoding, you basically try to define you can use the neural networks to predict the mean and the variance of the values at each step. And that can be autoregressive by like masking all future values. And assuming that this is the network that that defines the distribution of X, and what they try to do is like, can we make a continuous, can we make a flow between a random variable Z and X, such that basically the sampling part, instead of rolling out samples with the original like autoregressive distribution where you have to predict the exact probability of next value, you kind of rolling out by sampling from a random noise, and you transform that noise into this target distribution that is defined by these Gaussians. And we know that once we know this alpha and mu, this function here is always invertible, so it's naturally kind of a flow model where, like for any z, we can effectively compute the likelihood of x1. Yeah, but basically you can consider this as like a more flexible and general way of estimating the density of the data x by factorizing it with the autoregressive model, but at the same time you still use a random variable z to control the sampling and rollout and the density computation with this kind of flow, the flow formulation. So there are two types of autoregressive flows defined over this this setting. The difference is between like where you compute this autoregressive part. So the MAF used the normal, like the traditional kind of autoregressive formulation where you still like compute these alpha and mu's based on the x, the sample space, and you only roll out with the base distribution z, which z are independent Gaussians. So the forward mapping is, the sampling is still sequential and kind of slow, but the inverse mapping, basically if you get x and you want to like get the probability or the likelihood of x, the inverse mapping is very fast because we can like parallelize all invertible functions for every x to z, and we can compute it at once the likelihood of the observed sample. This basically they try to make the likelihood that estimation more parallelizable and faster, so we don't rely on some like sequential computation of the autoregressive likelihood. So inverse autoregressive flow, or IAF, is kind of the opposite of MAF in that you make the autoregressive part on the random variables. Basically the autoregressive part is computed based on the random variable or the base distribution, and this will, but this is basically the opposite of MAF, where the kind of the forward mapping is very fast because you have this determinism mapping from z to x in one shot. You can basically, for given z, you can immediately roll out a set of x with parallelization. But to compute the likelihood of x, it becomes a little bit harder. We need to solve this inverse autoregressive thing for predicting these alpha and mu, and so the inverse, the density, the likelihood estimation is more expensive. But these two are kind of completely complementary to each other. So if we interchange x and z, you basically get the inverse, the forward and the inverse mapping of each other. So now we talk about the application of these like stacked layers of flows or autoregressive flows, right? But one thing you can realize is we're still relying on particular choice of a set of layers. And again, we're in this discrete regime, like the discrete diffusion model, right? So we're limiting ourselves to kind of stacking on top of stacking these by design continuous normalizing flow layers to each ones, and we can define this kind of iterative process of transforming h of t into the next layer with this recursion of flow model, like the normalized flow model, that where f is basically the transforming function, the invertible function between the two. But if we similar to the diffusion, we effectively consider this process as a sequence of transformations that's applied to X again, right? And at each time we kind of keep track of the likelihood of X with some type of push forward function. And what is driving this transformation is this function of f, which is reused and defined at different time step in a discrete fashion. So similarly to how we continuarize the diffusion model, we can also imagine an unlimited stepped continuous normalizing flow, whereby we're basically considering continuarize this transformation process by defining the differential equation-like transformation, where essentially if you make the t plus 1 and t to be very small enough, you can consider it like ht minus 1 minus ht becomes like the delta t. And so we could continuarize this function here into the right-hand side, where we're trying to learn this kind of derivatives of h of t, or the flow of h of t, where we essentially at each step we have a function f that determines the change of position of the change of placement of h at each times. And this is very similar to actually the score that's defined in the energy, which is the derivative of the the derivative of the probabilities, and each time with respect to the x, and at each time step you're making these small changes, and the direction or the vector field is again decided by this function of x here. So this motivated as what we call continuous normalizing flow, which is the continuous extension of normalizing flows. And instead of using these discrete transformation and change of variable function, we now ended up defining a continuous transformation process, which is determined by a differential equation. And it's an ordinary differential equation because we have a fixed starting value. We have a deterministic trajectory that's uniquely defined by solving the differential equation here, where dx over dt is equal to this vector field function, which is what we define to transform xt to the next small time step. And if we start from some initial value, which can be a sample in the Gaussian space, and we apply this transformation for multiple steps by solving this differential equation, and after some time t, right, the points will got moved around and now move towards certain distributions. And we want to know in this transformation, we want to keep track of the probability or the density function, such that like we still have the nice property of kind of being able to track the likelihood. So given the analogy of these two continuous normalizing flows, we can think of like whether we can directly use the change of variable to keep track of this density function, right? So this basically the answer is yes, and we now derive this new version of change of variables. We call it instantaneous change of variables, or like continuous time change of variables. But essentially, instead of doing this kind of z equal to fz and doing this subtraction of log this, if we write z, the change of z with this differential equation, we can now derive that the log likelihood, the change of the log likelihood of the point also follows a differential equation. And that differential equation, the differential equation is defined by the divergence of the flow that would divergence of the applied the vector field applying to our original density function. And more specifically, if our flow is defined by f, right, then we can show that the log likelihood of the flow, the points, follows another differential equation where the derivative is the negative of the trace of the Jacobian of f. So like I think a very nice thing here is we get rid of the determinant of Jacobian and only rely on the trace of Jacobian. And the other thing is the f here is no longer needed to be invertible, because we kind of directly learning the direction that you're going, and it just needs to be bijectional. So bijectious. So with this continuous formulation, but essentially we're kind of saying that we have a way of transforming points from an initial distribution to some target distribution. And the way we transform it is by solving these unique ordinary differential equations. Like at every time step, we know exactly where the points are, and we know exactly where the points moves towards, and we know at each point how we can transform the likelihood such that we have inherently this vector field generates a probability at each time step t. So if we keep track of all possible samples defined in input in the source, and we can keep track of all possible points that it land up in every t, right? So at each t, we basically define a distribution if you apply this instantaneous change of variables by solving another differential equation. So which means that we have this continuous transformation of the probability, and we call it kind of a probability pass. So in flow matching or normalizing flow, continuous normalizing flow, we kind of have this you can consider it as a continuous time fashion way of defining a unique pass from a source distribution to a target distribution, such that at any time point in the middle, we kind of know we have a way to track of the distribution at t, and the only thing that we need to determine this flow is the vector field. Is this derivative or directional information that we need. All right, so I hope this is a good explanation. Is there any questions right now? Cool. So we're good. Okay, so maybe a simple question is like, is there any constraint on v? Like, is any function, if I just randomly take a function that give you some random value of t and xt, do you think that will be a vector field? Like, raise your hand if you think that can be a vector field. Okay, so everybody thinks it's not going to be a vector field. Yeah, I think the answer is yes. Like, not like any random function v defines a vector field. So the vector field, remember, like it has to derive this probability pass, which we can use to keep track of a family of probabilities from source to target. So we are moving it. We're moving the points, but at the same time, it also defines a probability, and that probability has to match the training data. And we will want to solve the function, the family of function that gives us that property. So we do have underlining. Remember, we're underliningly training a generative model that maximizes the likelihood. But instead of directly maximizing likelihood, we now have an alternative. So going back to how we train continuous normalizing flows, right? Before flow matching, very simple, very naive way of training continuous normalizing flow is simulation. Is what we said earlier. Like, just apply your current model and solve the ODE, and at the end of ODE, you'll be able to get the likelihood of the point. And we can just backprop through the ODE. And there are some way of doing it slightly more efficiently with like what we call adjoint method. But essentially, this is a very expensive process that we call it like simulation-based training. And this is like computing of this divergence, although it's not the full like determinant, but the trace of the Jacobian still like is still like very expensive, and you basically need to differentiate through the network multiple times, and which makes it accumulating a lot of numerical errors. So the simulation-based training, although it can work in some degree, is still not an ideal way. And if this remind you of the score matching case, right? In the score matching model, one thing we realize is we actually don't want, we don't actually need to maximize the exact likelihood by writing out the likelihood function. But instead, we can try to approximate the score function, such as if we follow the score function, we can exactly reproduce the underlying distribution. And that's exactly the same kind of mindset here. Because direct maximizing likelihood is expensive, we can think about an alternative where we just try to match the gradients or the vector field of this flow. So this is what we call flow matching, where basically we try to come up with efficient algorithm which we're able to compute and derive the ground truth vector field and try to train a model to fit and regress on that target vector field. So at the end, we learn the ground truth, we learn the model that is VT that we can use to approximate the ground truth vector field xt. Note that this is a function defined over all possible x and continuous time t. So like basically this, it is similar to like the score matching, right? You have a space domain of input. Every place in that plane, at every time t, you can end up being in somewhere in the space, and you want to learn a neural network that is general enough to fit that vector field, this entire field, and try to come up with some efficient way, such that at the end, if we learn it well, we get the ground truth. We're close to the ground truth vector field that transform the source distribution into the target distribution, which is the data. This sounds like, again, magic. This is actually, if we can get the ground truth vector field, then probably solve, we have like magic model. But similar to score matching, that function is not always tractable, and indeed it's not tractable. So basically, this target vector field that transform from noise to any possible data is very complex, and it's impossible to compute because we again need to like consider all possible like starting point and ending point, and there's also making a very strong assumption about the generalizability of the model. So in practice, we don't use this loss here, and I think the great invention of these flow matching model, which makes it thrive, is this observation that although the marginal probability path, which directly transforms the joint distribution of p of x, is intractable, the conditional path defined to transform noise into a single point in the training data is tractable. And by tractable, I mean we know exactly how the probability mass transform, and we exactly can define a probability path in analytical form, such that at each time point t, we know where the x is, and we know where the x should be heading towards in this vector field. So instead of directly solving the marginal probability path, which is, you need to marginalize the overall training data, we instead kind of make a sample from the training data and try to solve for this conditional vector, conditional path, the vector field for conditional vector, conditional path. And we call this vector field the ut of x given x1. So in flow matching, the 1 is it's the inverse of diffusion. 1 is usually the clean data, and unlike diffusion where 0 is the clean data. So instead of fitting on try to solve ut, we train a model to regress on the ut of x given x1, where we can define what ut is if we can come up with a creative way of defining the probability path, so we know the exact analytical form for ut. So basically, in the high level, the way we train the flow matching model is through first of all creating conditional probability paths from the training data, where we know that this conditional probability paths start with the p0 at t, where p0 is noise, and it land into target distribution, which is a delta distribution that has all of its mass focused on one of the training point x1, and that's the kind of the path that we're targeting. So if you look at this path here, we will try to fit the fit the UT such that UT generates a path like this. So we're starting from zero mean, maybe some various Gaussian, and we're transforming that distribution gradually by explicitly defining a Gaussian probability at each point of t, such that at the end, the probability ended up being very close to delta on x1. And secondly, we can find many probability paths from many different training data. So at the second step, we try to marginalize that vector field loss over the full data distribution by just sampling different training data and computing different conditional vector field. So this marginalization of vector field is a very important theoretical contribution of this paper, which we can't go into fully detail, but the great observation is if we define a marginal, if we define a loss which regress respect to the conditional vector field, and we marginalize this loss with the training data, and if we know that if we can train the UT that generates PTX given x1 well, then this marginalized vector field will also generate the marginalized probability. And secondly, if we use in practice, we use the second loss term here, where basically we sample different data points, and we try to fit the vector field of the conditional probability pass between that single point and noise. And we take the expectation here to marginalize over all the training data. And they show that, very importantly, these two training loss, although they're not exactly the same, these two training loss has exact same gradients, such that if you optimize the second one, you also optimize with respect to the first one. They have the exact same optimizer. So that is a great advance because we know how to compute the second term easily, and we know how to just basically take the expectation to marginalize this loss. So effectively, in the conditional flow matching, we're training with the second training objective here, which we call the conditional flow matching loss. And you will see that this V of t of x does not rely on x1, because we try to learn a single neural network that is used to fit all the possible conditional vector field of x1. So at the end, this V of t is actually learning the marginal vector field instead of just the conditional vector field. So the sampling of x given x1 is also easy, because if we define the probability paths, we know where the x are exactly. If we give the starting point and the end point, we know exactly where x are. So effectively in training, we instead of sampling x1 and sampling x given x1, we sample x1 and then we sample a noise, and we can directly interpolate between noise and the data to get where xt is. So essentially, we can. So essentially, we wanted to define the Gaussian conditional probability path. The conditional probability path, and one simple family of model that makes us gives us the capability of defining an analytical form for a legit probability at any t, which we can derive also the gradients of x for, is the Gaussian family. Particularly if we can define the probability path by defining the mu and the theta at every single time in between 0 and 1. And we can explicitly write down where x is. If we know that, if we define probability path like this, we know that for a given source data x and target data x1, these probability paths following this vector field function here, I will exactly land it in the position of this position, which is kind of the interpolation between x0 and x1 by applying this mu function and the sigma function. So effectively, we kind of derive this exact form of conditional vector field given the training data x1 by doing this interpolation. And this is the target that we're regress into. And this mu t and sigma t is what we call the probability path, basically how you define probability paths, coming up with different functions for mu t and theta t will define a slightly different probability paths. Yeah, I will get to this part because this will be part of the homework. So there are effectively we can use probability paths that are very similar to diffusion. Assuming like considering diffusion is also kind of making this adding noise and with multiple steps, you're kind of also defining like each step's a Gaussian distribution, because if you give a data point, right, a single data point x, you crop it, you get a Gaussian distribution as well, and therefore we can use we can mimic the similar probability paths in diffusion by defining either a variance exploding path or a variance preserving path. So the variance exploding path means that for any kind of data, we assume that kind of the mean is always focusing around the target points, and we're only kind of changing the variance. So we're shrinking the variance such that this path is kind of fixed in x1, and we're shrinking the variance such we're starting from somewhere completely noise and but then shrinking towards the target delta distribution. And variance preserving path means that we start from a Gaussian noise and we move the mean along the path, but we keep the variance to be the same. So basically we have a delta function here, and we have maybe some Gaussian like random Gaussian here, and we just like move it towards the end. And so this is kind of not exactly in the straight line, but in diffusion, if we follow some of the diffusion scheduling, you will see that it ended up defining something that's like this. It's not exactly this, it's kind of like this, like if you compute it, but this is because of the kind of the definition of diffusion, and which makes this path ended up being not a straight line. But the good thing about flow matching is we can define like we can define in this mu and theta in any way we want, as long as it's differentiable with respect to time. So at the end, people find this what we call optimal transport path being very effective and intuitive. So instead of going through this like curved path, we directly interpolate between noise and the data, the mean, right? So the mean here, you can see the mean is a straight line interpolation between the noise and the data, and we kind of gradually shrinking, the variance, such that at the end I end up with a very tiny variance. So this OT path is effectively the very straightforward and elegant way of defining probability path, and it's only possible because it's flow matching. And so at the end we kind of effectively in the training data we're using this OT path with this formula here to derive the U of x given x1. So we ended up training, we could consider like, basically if we sample x0 and x1, I will exactly know where the xt is by doing the linear interpolation, and I will exactly know what my variance is, which is a kind of t square. And they show that these probability paths is the optimal in terms of kinetic energy, basically like how much movement you made to transform the point from source to target. Note that this is a conditional probability path, so